Hey everybody, this is Mr. Brooks again. So today we are going to get into section 11.3 with the integral test. However, before I wanted to begin, I wanted to go over a couple of things that we have covered so far up to this point dealing with series. And it's a good thing to have these memorized. So this way, as you go through each one of these sections, I am going to do this every single time. You're going to get tired of me hearing of this, but again, as you repeat these more and more and more, it'll eventually sink in. And so, to start things off, what is a series? A series, by definition, is a sequence of partial sums. Okay? So, if we're going to look at this, just to give us a very brief example, the series is summation notation, as n goes from 1 to infinity, of a sub n. This is the formula of the series, which is equal to a1 plus a2 plus a3, and so on. So its sequence of partial sums, S1 would look like A1. S2 would look like A1 plus A2, and so on. So this sequence of partial sums represents this series, okay? Well, when does a series converge? Well, a series converges when the limit, as n approaches infinity, of the sequence of partial sums, S of n, is equal to some value s, and when the sequence, okay, so again, sequence converges. Okay, so these are the two criteria in order for a series to converge. We're going to talk about the sequence of partial sums when we're talking about S sub n. Okay, so what are some known series that we've talked about? Well, there's only been a couple that we have talked about. The geometric series is first, and we have a couple different forms depending on when our index starts. So if our index starts at 1, we are in the form AR to the n minus 1. Okay. And if it starts at 0, it's of the form AR to the n. Okay? The nice thing is when these converge, when the absolute value of R, okay, is between 0 and 1. And diverges elsewhere. And you could say here the absolute value of R is greater than or equal to 1. Okay? The nice thing about both of these is once you have those in those formats, either when n is equal to 0 or n is equal to 1, both of these guys, if it converges to a very specific value of A over 1 minus R. That's only if it converges. All right, the next series we have, we use a smaller sequence in order to talk about this one. So this is the harmonic series. It is of the form as n goes from 1 to infinity of 1 over n. It's a very simple series here. All right, it is of the form 1 over 1 plus 1 over 2 plus 1 over 3, and so on. Well, we found out using a smaller sequence that this series diverges. The nice thing is if we come across this series again, we get to use this idea that we know that it diverges without having to prove it again. All right, and then from section 11.2, we also talked about our very first test, talking about if a series diverges or not. Now, this test here is only specifically for talking about divergence. And what has to happen with it is if the series A sub n, all right, if A sub n, actually let me rewrite that just a little bit. If the limit as n approaches infinity of A sub n does not equal 0, or the limit of A sub n as n approaches infinity does not exist, the series, this again the summation of a sub n, as it goes from 1 to infinity. It can go from 0 to infinity as well. So as long as these two things happen, if it doesn't equal 0 or it does not exist, then we could say that the series diverges. Okay, so that's what we have dealt with so far. All right, so now into getting into 11.3, kind of went backwards a little bit here, but I wanted to first talk about this particular series here. So this is the series from 1 to infinity of 1 over n squared. So we can see its form here of 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared and so forth. So we could use a computer and look to see that the partial sums are approaching the value of approximately 1.64 as n approaches infinity. So if we wanted to, we could see this, but that's not a true way to talk about if a series converges or not. So it does appear that that's going to be the case, but that might not be. So this is where the integral test is going to become very important. So here, what I've done is I've actually built this series in a graph. All right, this is our first value of 1 over 1. So I used a base of 1 for each one of these rectangles and used the function value, okay, as its height. So I get 1 over 1 squared, which is 1. So this is the area of 1. The next one would be a base of 1 and a height of 1 over 2 squared. So 1/4. And notice, if I add these two together, I get 1 plus 1/4. And in fact, if I continue this pattern, here's 1/9, and so on. I can actually build this series using geometry, okay? The integral test here is saying, okay, if there is a function that I can use to contain this particular series, then I can use an integral to work with it. So that's why the integral test, okay? And in fact, if I use the function (1 over x squared) to contain it, I'm good. And the nice thing is we do have this ability to be able to talk about the integral on an infinite interval. So in fact, if I look at the integral from 1 to infinity, and there's a reason I'm using 1 here, we're going to talk about that here in just a second, of 1 over x squared, we've dealt with this before. This is going back to section 7.8 when we dealt with improper integrals. Okay, so with this one, I could rewrite it as a limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. Okay, evaluate it, you get the limit as t approaches infinity of negative 1 over x from 1 to t. All right. And now I just plug in my values for my integral. So I'm going to get the limit as t approaches infinity of negative 1 over t plus 1. And a better way to write that is the limit as t approaches infinity of 1 minus 1 over t, which is equal to 1. All right, so now backtracking a little bit. I left off a very crucial piece here. So I started my integral at 1. The nice thing is I know this value here. So if I can find out that the area underneath this curve converges, then this sum here, the sequence of partial sums starting at this point on, will also converge. And in fact, it does. And you just add this finite value of 1 to it. So this is the idea of the integral test. Hey everybody, Mr. Brooks here again. So last time we talked about starting into 11.3, the integral test. So I want to go back over this example real quick of what we've done because we're going to go over another problem here in just a second. But I want to finish up exactly what we were talking about, why we're able to do this. So, first of all, I built the rectangles based upon a base of 1 and a height based upon each of these values here to generate a geometric argument for this particular series. And so what I've done is now I have looked at, on the integral from 1 to infinity, I used the integral of 1 over x squared. So with that, we found out that this particular area underneath the curve converges. Okay, and I did leave off this interval from 0 to 1, and we're going to talk about that here in just a second. But the big important thing here is that we saw that this converges. All right, coming back over. So we found out that the total area of the rectangles are less than 1 plus the area underneath the curve. Okay, so 1 plus 1 is 2, obviously. Therefore, we can specifically say that the partial sums, so the reason why we're talking about partial sums, again, coming back over here, is we add each one of these rectangles to the next. That is our sequence of partial sums. So we can say specifically here, the partial sums are bounded. Again, we're talking about a sequence here, so remember what it means to be bounded. That we have a value that is greater than or equal to that series. And also, if it's bounded, that means it's bounded above and below by a particular value. So in this case, it's bounded above by 2 and bounded below, technically, by 0 if we wanted to. Or if we wanted to push it a little bit further, we could say even 1. Okay? Well, if we know it's bounded, that's good, but that doesn't mean that it converges. Okay? So we're going to get to one further step. The value of the partial sums is increasing. Now, we're sure about that, which would make it monotonic. Okay, well, let's talk about that. Well, yeah, if I add 1, then a fourth to it, then another value, these are all positive, then yes. As we increase the number of terms that we're adding to this, as we look at each next value of the sequence of partial sums, we see that its values are increasing. Well, it's bounded and increasing, or monotonic. Well, that means we actually know that this sequence is going to converge. Thus, by the monotonic sequence theorem, the sequence converges. And not only the sequence converges, it's the sequence of partial sums, which means the series converges. So again, the sequence of partial sums converges. Thus, and I know we got thus in there twice, but that's okay. Thus, the series converges. Okay? So that's a good thing. That's exactly what we wanted to show. All right, so the next one. I want to consider this problem. All right, this is the series of 1 over the square root of n. Again, the values are as shown. 1 over the square root of 1 plus 1 over the square root of 2 and so forth. I want to see if we are approaching a particular value because it fits that we got 1 over n squared. That should be good. So what about 1 over n to the 1/2 power? Well, if we looked at the sequence of partial sums, and I notice here that I went very far out. We're going to start with looking at the 5 first terms, and then the 50 terms, and then 100 terms. And then I'm going to add a 5,000 of those. Again, I didn't do this by hand. We used a calculator or a computer program to do that for us. Well, if we look at these are approximate values when they're added. We're going to notice something. Well, when I add the first 5 terms, I get 3.23. Nothing horrible. Then I get 12.75 approximately. Then with 100 terms, I get 18.59. Then with 5,000 terms, I get 139.97. So this isn't pointing towards something. Notice as I increase my values of n, and I've done several large values of n here. Our sequence values are increasing still, and they're not approaching a particular value. So this could kind of lead us to the idea, oh, this guy looks like he is going to diverge. Well, this is where we're going to use this idea that we dealt with the first problem onto this one. So here I've already started building my argument here. So again, I've given a base of 1. Here, this is going to have the area of 1 over the square root of 1. Okay? This will have an area of 1 over the square root of 2, and so forth. 1 over the square root of 3, and 1. Okay? Well, let's try to find a function. Well, a good function here would just be 1 over the square root of x. Well, if I do that, here's what's going to happen. Notice here, the way I've drawn this. Yes, you could make the argument, well, if we shifted everything, there's a reason I'm going for this. Notice with this one that we are overestimating what the area underneath the curve is from 1 to infinity would be with this particular sequence. Okay? So, if that's the case, and I show that the area underneath the curve of 1 over the square root of x diverges, that this sequence is also going to have to diverge because of that. All right, so let's test that out. So right now we can make the argument that s of n is greater than the integral from 1 to infinity of 1 over the square root of x dx. Correct? Okay, so we've made that argument. So let's solve this right-hand side, see what's going on. Well, when I do that, I'm going to get the limit as t approaches infinity of the integral 1 over t of 1 over the square root of x dx. Okay, so we can bring that up, make it a negative 1/2 power, add 1 to it, and so we are going to get, in the end, the limit as t approaches infinity of 2 square root of x from 1 to t. Okay, well, plug it in our values. I get the limit as t approaches infinity of 2 square root of t minus 2. Well, as 2 approaches infinity, or sorry, as t approaches infinity, this negative 2 is not going to have much of an effect on it, and in fact, this is going to blow up to infinity. So notice this has unbounded behavior, represented by the infinity sign. So we can say that this improper integral diverges. Well, going back to talking about sequences, if a smaller sequence diverges, then the larger one has to diverge. Likewise, when we dealt with improper integrals, if we found out we had a sandwiched function between the x-axis and another function, if that's bottom function, if its area diverges, then the top function has to diverge. Okay? So therefore, the series diverges. Okay? And that's what leads us into our integral test. So our integral test is going to be using these types of series, okay, or these types of functions. Now we've got to be very careful when we're dealing with these guys. Okay? Just like with a lot of tests, we are going to have very specific rules that we have to follow in order for them to work. So the integral test is as is. Stated, suppose f is a continuous function and not only is it continuous, we're actually going to add a little bit more criteria to it. We're going to say it's continuous, positive, and notice what else that we've had with these particular examples. What do we see overall with each of these functions? We saw that they were also decreasing as well. So we're very, very limited on what we can deal with here. So we have a continuous positive decreasing function. On some interval. And we're going to say 1 to infinity. Okay? And let f sub n equal the formula of the series, okay? So that means for every integer value, we are going to be generating this particular value of the series, okay? So when n is equal to 1, we're generating the first value. When n is equal to 2, generating the second value, so forth. Then, so once we have satisfied these two hypotheses, or these several hypotheses, that we have a continuous positive decreasing function on some interval, on an infinite interval, and we have that the function is equal to the series, and that's easy to come up with, since for the most part, we could just plug in an x for every n that we see. Then we have two cases. Step 1, if the integral from 1 to infinity of f of x dx converges, then so does the series. Of a sub n as n goes from 1 to infinity. That's great. Step 2. If the integral diverges, then so does the series. This is perfect, because with this one, if we meet all these criteria, then I can tell you exactly if the series is going to converge or diverge. Whereas the test for divergence only talks about, is the series going to diverge? Okay, and in fact, it's not that well either, because we have seen with the harmonic series, its limit is equal to 0. However, that doesn't mean necessarily that it converges. Okay, so this one is a little bit nicer, but we have to have very, very specific hypothesis to go with this. Okay, so in the next video, I'm going to go over a couple of examples to demonstrate the power of this. Hey everybody, Mr. Brooks here again. So last video we talked about the integral test and finally actually developed our integral test. And so I really want to go back over it just a second. I know it's just like a couple minutes ago that we just talked about it. So suppose f is a continuous positive decreasing function on an interval from 1 to infinity, and let f sub n equal a sub n. Then either if the improper integral converges, then the series is going to converge. Or if the improper integral diverges, then so does the series. Okay, so I wanted to go over a couple of examples of this, of how to walk through the process, because the easy part here is actually the improper integral part, in my opinion, because we know how to deal with those guys. Yes, it's a limit. There are some painstaking tests to go through that, but it's not that bad. We've dealt with them before. It's this piece here. Continuity is not bad to talk about. We've dealt with that before. Positive, yeah, we just can, we're going to be dealing with a positive interval, so that's good. So that helps us out with a little bit. It's the decreasing part. So we are going to talk about that a little bit more in depth today, just to go ahead and get that solidified. All right, so going back over here. So I want to determine if the following series converges or diverges. Okay, the first one we're going to look at is this series from 1 to infinity of 1 over 3n plus 1 raised to the 4th power. All right, so we need a function that is going to behave just like this particular series. So again, the nice thing about this is we can really just plug in an x value for n, and we're okay with that. So my f of x, in this case, is going to be 1 over 3x plus 1 raised to the 4th power. Now we have to talk about, well, is this guy continuous on the interval from 1 to infinity? Yes. In fact, 3x plus 1, this guy is only 0 when we're dealing with negative values. Okay, so we know it is continuous on the interval from 1 to infinity. We can actually blow that up a little bit more, but again, I just want to go from 1 to infinity, nowhere else. All right, 2. Is it positive? Okay, well, Yes, it is positive. We have 3x plus 1, and we're plugging in positive values, and then we're raising it to an even power. So yes, this guy is positive as well. Now it's the decreasing part. We have to prove or show. So this is the one I always want you to show. Continuity, yes, you need to talk about it and if it's positive or not, but the biggest one is I want you to show that it's decreasing. Yeah, we're dealing with a fraction here. More than likely it is decreasing, but let's see how we can talk about it. Okay, I could look at a table of values, but that's not definitive enough. What we can do is look at its derivative. Okay, so another way that we can write this is 3x plus 1 to the -4th power. The reason I'm doing that is so we can have a nice chain will pop up here in just a second. All right, so let's look at its derivative. Well, when I take the derivative of this function, I am going to get -4 times 3x plus 1 to the -5th power times the derivative of the inside function, which is 3. Okay, another way to write this is -12 over 3x plus 1 to the 5th. This guy is decreasing because it has a negative derivative on the interval from 1 to infinity. And then this is how we can show that it is decreasing. So in all else fails, if you try to think about some of the other things that we did with sequences before to show that a sub n plus 1 is less than a sub n, that is a technique that you could use. Here, a derivative is a little bit quicker in that sense because there's a lot more algebra, in my opinion, on the inequality. Okay, so now that we have shown that this is a continuous positive decreasing function on the interval from 1 to infinity, and we chose this function specifically by just plugging in x for n. So we know for every integer value, we're going to generate this, the series values. Okay, so that means we only have one step left. Let's look at the improper integral. Okay, so we're going to do the improper integral from 1 to infinity of 1 over 3x plus 1 to the 4th dx. This is equal to the limit as t, let me erase that just a little bit, as t approaches infinity of the integral from 1 to t of 1 over 3x plus 1 to the 4th dx. Okay, well, this is not bad. I see a simple u substitution that's going to pop up out of this. So let's do some work to the side real quick. That's all what I've always used in class is that WTS. So in this case, just looking at this integral, I see a very good u substitution is u is going to be equal to just 3x plus 1. All right, so du is going to equal 3 dx. So that means a third is going to pop out of this times the integral of 1 over u to the 4th du. And we can actually just go ahead and solve it here. Then that way I can plug this in. Now you could change the bounds, which is perfectly fine. To keep this in terms of u, you just plug in t for your upper bound, plug in 1 for your lower bound, and you would keep those there. So you would end up with 4, and then you'd have 3t plus 1 as your upper bound. But in this case, we can go ahead and figure out what the antiderivative is and then plug it in into here in just a second. Okay, so I'm going to get that 1/3 out. Okay. And then this is u to the -4th power, so we're going to add 1 to it. So we get -3 divided by -3. So in the end, we're going to get -1/9 u to the -3. Or another way to write this is -1 over 9 times 3x plus 1 to the 3rd. Okay? Next, we need to plug in this into our limit. So I'm going to take the limit as t approaches infinity of, and I can bring that -1/9 out if I wanted to. So let's actually go ahead and do that. Because it's a constant multiple, I'm going to bring out this -1/9 out in front. Okay, and if this goes to a finite value, then we're okay. And if it goes to infinity, we're still fine. Okay? So, with that being said, I'm going to get 1 over 3x plus 1, the quantity cubed raised from 1 to 2, or 1 to t. Okay, plug in our values. Make sure to bring that -1/9 out in front still. We're going to get the limit as t approaches infinity of 1 over 3t plus 1, the quantity cubed, minus 1 over, well, 3 times 1 is 3 plus 1 is 4. All right, so when we're looking at that, as t approaches infinity, what's going to happen to this denominator? Well, it's going to get larger and larger and larger. And we've talked about this before. If the denominator grows up and blows up, and the numerator stays the same, then this is going to go towards 0 for this one. Which leaves us -1/4 times -1/9, which gives us positive 136. Which means what? Well, that means by the integral test, the series converges. Okay, so I'm being very specific here. So what gives us that authority to talk about convergence or divergence? Well, in this case, it is the integral test. This is very nice. So again, because our improper integral converges, then the series converges. So with all of your solutions, I want you to be very specific on what is happening. What gives you that authority to say, this is a convergent series, this is a divergent series? Okay, so the next one. B. We have 1 over n squared plus 1. So first of all, we can clearly see here that this is going to be positive. So if we look at f of x, again, what are the criteria for the integral test? Again, continuous positive decreasing. Okay. Again, it seems almost like cheating, but this is exactly what we're going to be doing. I plug in an x for n. Okay. This is never 0 in the denominator. Okay. So therefore it's continuous everywhere. All right. X squared plus 1 is never negative for a real valued function. So it's positive. And we need to show again that this is going to be decreasing. All right. So I'm going to take the derivative of this. Again, because a lot of us do not like using the quotient rule, which is okay, that's fine. There's ways around it. We can use a product rule, using a chain rule as well, so that's what we're going to do here. So I'm going to get -1 times x squared plus 1 minus 1, so that's going to be -2 up top, and then I'm going to take the derivative of the inside, which is 2x. So in the end, I get -2x divided by x squared plus 1, the quantity squared. Okay, that means this is always positive here. We are plugging positive values for x. Therefore, this is going to be negative. So this is less than 0 on the interval from 1 to infinity. So therefore, this is decreasing. Which means I'm ready to use the integral test. So now that I've satisfied all my conditions, I'm ready to apply the integral test. So I'm going to look at the integral from 1 to infinity of 1 over x squared plus 1 dx. And now I'm going to look at the limit as t approaches infinity of the integral from 1 to t of 1 over x squared plus 1 dx. Well, does this guy look familiar? Yes, it should. This is arctangent, x squared plus 1. Okay? So, I get the limit as t approaches infinity of arctangent of x, evaluated from 1 to t. Here I'm going to get the limit as t approaches infinity of arctangent of t minus arctangent of 1. Well, arctangent of t, well, as t approaches infinity, remember what's going on. Arctangent has two horizontal asymptotes. As we approach positive infinity, arctangent is approaching pi halves. And arctangent of 1, well, that's the same thing as asking, well, when is tangent equal to 1? And that's at pi fours. So in the end, we find out that our definite integral is equal to pi fours, or sorry, improper integral, which is convergent. Therefore, by the integral test, again, I want you to be as formal as possible with this. The series, and here just to make sure that we're talking about the same one, converges. Again, talk about what is giving you that authority to say that this series converges. And that's it. That's all you have to do. So we've seen examples of where it diverges. We've seen examples where it converges. And this is all you have to do. So the big thing that you, again, have to check is to make sure that you're dealing with a continuous positive decreasing function. And the hardest one probably of those three is the decreasing part. But the nice thing is you have derivatives as a backup plan. Okay? And that's what we're going to talk about today. Next video, we're going to talk about a family of series called the P series and talk about where they converge and diverge.